Today in this video I am going to explain Euler's theorem. So the statement is, if f z fxy be a homogeneous function of degree n, then x del z upon del x plus y del z upon del y is equal to nz, where n is the degree of the function. Now we are going to prove it. Proof: if z is equal to fxy is a homogeneous function of degree n, then it may also be written as z is equal to x raised to the power n f y upon x. Let it be equation number 1. Now, differentiating equation 1 partially with respect to x, we get del z upon del x is equal to first function as it is, x raised to the power n, differential of f y upon x as f dash y upon x multiplied by minus y upon x square plus, now differential of x raised to the power n x raised to the power n minus 1 into f y upon x multiplying both sides by x, we get x del z upon del x is equal to minus x raised to the power n minus 1, because there is x raised to the power n and in denominator x square, and if we multiply by x it remains x in the denominator, so we have ultimately x raised to the power n minus 1 y as it is, and f dash y upon x plus n x raised to the power n, because there is only one negative power, so and multiplying by x we have only x raised to the power n f y upon x. Let it be equation number 2. Now differentiating equation 1 partially with respect to y, we get because there is x to the power n which is taken as constant on differentiating partially with respect to y, so we need not to use product rule in this. So we have del z upon del y x is to the power n as it is, as constant, and differential of f y upon x with respect to y partially. So f dash y upon x, because it is arbitrary function, multiplied by differential of y upon x with respect to y, 1 upon x, because the differential of y is 1 and x is constant. So we have x is to the power n minus 1, because there is x is to the power n in the numerator and x in denominator, f dash y upon x, let it be, multiplying both sides by y, we get y del z upon del y is equal to x is to the power n y, x is to the power n minus 1, y, f dash y upon x, because on multiplying by y, left hand side y del z upon del y, and on the right hand side x is to the power n minus 1 was there, so x is to the power n minus 1 y, f dash y upon x, let it be equation number 3. Now adding equations 2 and 3. This is equation 2, this is equation 3. So on the left hand side we have x del z upon del x plus y del z upon del y is equal to, on the right hand side, minus x raised to the power n minus 1 y f dash y upon x plus x raised to the power n minus 1 y f dash y upon x plus n x raised to the power n f y upon x. These two terms are identical and having opposite signs, negative and positive, so cancelled. And we have x del z upon del x plus y del z upon del y is equal to n x raised to the power n f y upon x, the only term left on the right hand side. Now in this expression, x raised to the power n f y upon x is equal to z from equation number 1. So in this equation we may replace this expression by z. So finally we get x del z upon del x plus y del z upon del y is equal to nz. Hence we have proved Euler's theorem of partial differentiation.